Good morning, everyone, and thank you for being here. My name is Athanasios Valomenos from LIBRA AI Technologies. Today, I will present our work on bridging raw sensor data and business intelligence system through an AI-driven metadata-aware mapping approach. It is about getting messy industrial sensor streams into a BI system automatically, but with safety. Let me start with why this matters. Industrial BI and decision support systems run on heterogeneous sensor data, and these streams never look the same. They differ in sampling rate, in units, and in how columns are named, and very often the names are multilingual, abbreviated, or simply missing. Today, this is done by hand or with static rules, and it does not scale across sites or sensor families. So, we frame it as a learning problem. The input is a univariate signal, one of 100 hourly samples plus an optional column length string as metadata. The labels are the cross product of sensor type and unit, more than 40 valid pairs. We learn a function that ranks these classes, take a top prediction by default, and keep the top 5 for expert review when needed. The question is whether a single end-to-end model can use both the temporal signal and the textual metadata while staying confidence aware so a human can step in. Briefly, where this sits in the literature. Classic schema matching like Valentine is strong on static tables but not built for temporal data. Time series classification gives us tools such as Rocket and Transformer encoders like Chronos. There is work using column names and units as semantic context, and recent LLM-based annotation of tables, such as Steel LLM, but again limited to static data. The gap we address is an end-to-end framework that fuses learned temporal representation with multilingual texts, embeddings for raw sensor streams, and exposes per prediction confidence for human-in-the-loop validation. Here is the architecture at a glance. From each window, we extract 3 complementary feature sets. Rockets gives a randomized feature vector. Chronos gives a contextual time series embedding, and Mini-LM turns the column name into 348-dimensional text embedding. We simply concatenate this into one vector, and the gradient boosting classifier maps it into probability over the 40 plus classes. We take the argmax as the top 1 prediction, and we keep the top 5 for review. One practical point: if metadata is missing, the framework degrades gracefully. We just drop the text below. A bit more on the 2-time series encoders because they do different jobs. Rocket applies a large bank of random convolutional kernels with learning and pools each by its max value and the proportion of positive values. It is very good at local structure, bursts, peaks, and micro patterns. Chronos is a transformer pre-trained on time series tokens, here in a tiny configuration for efficiency, and it captures long-range behavior, of course, and periodicities. The point is that they are complementary. Fusing the two improves top 1 accuracy by about 4 to 5 percentage points over Rocket alone across both classifiers. On the metadata side, we use a multilingual Mini-LM sentence transformer producing 348-dimensional embeddings because it is trained on paraphrased data. It is robust to abbreviations, synonyms, and non-English column names, and we add a small multilingual synonym dictionary for the most variants. Fusion itself is deliberately simple. There is no learn alignment, just concatenation, and we let the classifier exploit the block structure of the combined vector. For classification, we compare XGBoost and IGBM, grid search on the validation split, and the output is per class probabilities over our 40 plus type and unit pairs. Now the data and the protocol which we will use are very strict. We use 8 public sources, for example City of Chicago, MPI, GINA, and DEPA, plus 1 private industrial dataset from a mining industry with multilingual and partly missing metadata. Preprocessing resamples everything to 1 hour, harmonizes units, and applies the synonym dictionary. The key choice is the split. It is source disjoint, so no source appears in the partitions and the model cannot just memorize a source. We report top 1, top 5, and F1 measure averaged over 3 random seeds. These are results. The best configuration, the Rocket plus Kronos TAF5, T5 with light GBM and column names reached top 1 accuracy of 86% and F1 accuracy 86.5% and top 5 above 98% on a problem with more than 40 classes. The ablation tells a clean story. Kronos on top of Rocket buys 4 to 5 points of top 1. Column names are buying roughly 2 more. Top 5 stays above 97% in every configuration. Light GBM matches XBoost on accuracy while training faster. That very high top 5 is what makes the human in the loop practical. Because even when top 1 is uncertain, the correct answer is almost always in the shortlist. Let me make this concrete with mining case study. Here we evaluate on the same site, but on temporally disjoint unseen segments, so it's genuine generalization test. Flow underscore LS is predicted as flow in liters per second with probability 99%, so it is auto-accepted. Altura, a Spanish column name, is correctly mapped to height in meters, which shows the multilingual transfer is working. And normal LF comes back at only 46%, so it is flagged for an expert rather than trusted. The operational rule is simple. High confidence is auto accepted. Ambiguous cases go to an expert who validates the top 5 set. A few honest limitations. It's that we assume a closed set, so genuinely new sensor types are only flagged by low confidence, not detected. We treat columns independently, so relations between co-recorded sensors are not modeled. The auto-accept threshold is empirical, not tuned against the operational cost. The hourly window may undersample fast transients. Future work follows directly. Out of distribution detection in the fuse space, an active learning loop to grow the taxonomy, multivariate fusion across channel, and streaming inference. The human in the loop step is what absorbs the residual error from all of this. To conclude, we presented an end-to-end framework that maps raw sensor windows with optional metadata to sensor type and unit classes. It fuses temporal and schematic information. Rocket, Kronos, and multilingual mini-LM, which are empirically complementary, wrapped in a confidence-aware decision rule with top 5 expert validation. We reach 86% top 1 and 86.5% F1 accuracy on a 40-class problem. And we validate it, of course, in a real temporally disjoint mining deployment. It is deployed as a streamlit application, upload the CSV, get automatic detection and top 1 and top 5 prediction. The expert can validate and it may land in the BI database. Thank you for your attention. I would like to say that this work was supported by the European Union's Horizon Europe program through the MASTERMINE project.